Alright, let's get a lot of practice here with the right hand rule. Here we go. So number 1, what did you get? Did you get into the page? Yeah? Good. Remember, into the page is shown with an X. In case you're not sure, here's my hand doing it, which is a little bit tough to see. So here's the paper. You can just barely see it, right? The chart is moving to the top of the page. Here's my pointer finger to the top of the page. My middle finger is pointing towards you, which in this orientation is with magnetic field. My thumb is jabbing the paper. It's really tough to take a hand selfie like this, but that's what should be happening here. All right, so your thumb should be pointing into the paper. All right. Number 2, did you get out of the paper? Yeah? Good. Okay. Here's my hand doing it. My pointer finger is pointing at the top left-hand corner. Curl my fingers all the way this way to the bottom of the paper. Stick your thumb out. Remember, you have to be sticking your thumb all the way out. You got to make a right angle between your pointer finger and your thumb. You should see your thumb is pointing out of the paper. We draw that as the dot. You can put a circle around it. That's sort of optional. The dot is really the important part here. That's out of the page. Excellent. All right, number 3. Did you get into the page? Yeah? Did you? Let's see. Because, wait, why have my pointer finger pointing this way? Oh, it's a negative charge. Look, there's only like one trick in this whole topic, and that's it, right? It's going to happen again. Don't get tricked by it. So remember, you have to do something different. So what I chose the velocity thing. I could say a negative charge moving to the bottom of the page, and the same as a positive charge moving to the top of the page. So I got my pointer finger at the top of the page because I always follow the positive charge. I curl my middle finger to the left, which is the direction of the magnetic field. I stick my thumb out, right? So in this case, it should be out of the page. Now, if you had done it like normal, you would have gotten into the page, so you could have just done it like that and then flipped your answer, but really you should be getting out of the page. Now, of course, you have your options, right? Either change the velocity or do the right hand rule like normal, flip your answer, or you could use your left hand. I don't like to use my left hand. I always want to use my right hand, but you have that option. But again, there's only one trick. Don't get tricked by it again. All right, how about number 4? Number 4, did you get to the bottom of the page? Yeah? All right, hopefully. Well, maybe you're a little confused, but look, here's the velocity vector. How is that pointing? That's out of the paper, right? So to do this, you kind of have to have your pointer finger pointing out of the paper. There's velocity out of the paper towards you. Then your middle finger or other fingers curl to the left, and your thumb, which has to make a right angle with your pointer finger, is pointing to the bottom of the page. Yeah. All right, good. How about number 5? Ooh, what you got for number 5? Yeah, number 5 is a little bit of a tough one because the charge is moving to the left, and the field is all the way to the right. Ooh, you'll really hurt yourself if you try to do this, right? You can't. Ooh, that's painful. But wait a second. What's the angle between the velocity and the magnetic field? Please tell me you didn't say 0 degrees. I hope you didn't say 0 degrees, right? It's 180. It's 180 degrees. They're exactly opposite of each other. Sine of 180 is 0. Remember, if a charge moves with the field or against the field, there's no magnetic force. What about number 6? What'd you get here? All right, so here's our velocity vector. Which way is it pointing? Into the page. Oh, but it's a negative charge, right? Negative charge point moving into the page, like a positive charge moving out of the page. So when you do our right hand rule, the charge moving out of the page. Which way is the field? Ooh, the field of these dots also. That's also out of the page. No magnetic force, right? Because the charge, the positive charge, imagine is moving directly with the field, or here a negative charge moving directly against the field. No matter what, it's not crossing any field lines. No magnetic force. All right, how about number 7? What's this? Ooh, now it's a wire with current, but things don't change because we've got the current and it's conventional current. Right, so what did you get? Did you get to the left? I hope you did. Yeah, here we go. So our charge is moving to the top of the page. Field, ooh, here's our field lines. They're pointing into the page. That's my fingers going here. Stick your thumb out, making a nice right angle. Thumb is pointing to the left. This whole wire feels magnetic force to the left. All right, how about for number 8? What'd you get here? Did you get into the page? I hope you did. Let's take a look. All right, here's my hand selfie again. My pointer finger is pointing this way which is to the left of the page, right? That you can't quite see it, but here it is to the left of the page, like so. My middle finger is curled to the top of the page. I got to stick my thumb into the page. I'm jabbing the paper with my thumb, my right thumb, so we got to point into the page. There it is. Good. Okay, let's go back into your handwritten notes. We're going to take a look at a useful application of a magnetic field, a device known as a mass spectrometer. Here's the setup. Let's say we're looking down at this, and there's this big sort of box. That's the gray confines of the object. And then there's this opening where we introduce some charged objects moving. So we have a positive point charge. It's going to move to the right inside a uniform magnetic field. That's rather important to a uniform magnetic field. In this case, all these X's show the magnetic field pointing into the page. And the walls of the mass spectrometer are a detector, which means anytime this charge hits the wall, the light, it's going to light up so we can see where it hits. We see what happens. All right. So we have a positive charge moving to the right inside a magnetic field. You've drawn this in your paper. You've drawn this in your notes. Go ahead and do a right-hand rule and figure out which way this charge will feel a magnetic force. Okay, so the charge is moving to the right, fills into the paper. We should feel a magnetic force to the top of the page. Are we getting that? Top of the page? There it is, top of the page. All right, very good. All right, so now it's going to be deflected, right? So let's see what happens next. It's not going to move to the right anymore. It's going to be deflected sort of the top of the page. So here it is sometime later. So go ahead and do another right-hand rule. Figure out the direction of the magnetic force now. So the charge is moving to the top right-hand corner of the page. The field is still into the page, and now our thumb is pointing to the top left-hand corner. So there's the magnetic force. So it's going to be deflected again. And so let's draw some time later. Here it is now, moving to the top of the page. Go ahead and do right-hand rule again and figure out the direction of the magnetic force. Did you get to the left? I hope you did. Charge moving to the top of the page, field is again into the page, your thumb is pointing to the left of the page, and now it's going to sort of be pulled back here. It's going to follow a circular path. Look at this, it's tracing out part of a circle. Oh, the force is always at right angles to the motion, always pointing into the center. What's the name for that force? Oh, that's a centripetal force, isn't it? Right, yeah. And then the charge is going to hit here, the screen's going to light up, and we can see the dimensions of this circle. We can measure the diameter of this circle, for which we can get the radius of this circle. Ooh, so we're dealing with circular motion again. Centripetal force. In this case, the centripetal force is provided by the magnetic force. It's a magnetic force that's always pointed to the center because that's the nature of the magnetic force. It's always at right angles to motion, so we can't actually change the speed of the object. We'll just change the direction. Okay, so F sub m, should we be using QVB sine theta or ILB sine theta? Right, QVB sine theta. There's no wire with current here. These are clearly a point charge we're looking at, right? So it's going to be QVB sine theta over here. Ooh, what about for F sub c? What's the equation for centripetal force? Remember? mv squared over r. Yeah, good. Okay, so here we go. So we write QVB sine theta for magnetic force, mv squared over r for centripetal force. We set them equal to each other, and then we're just going to, well, what's theta? Ooh, what's theta? Where do we measure theta? Right, between V and B, and the velocities are always in the plane of the paper. The magnetic field is always into the paper. That's always going to be a 90-degree angle. Sine 90 is 1, so that's going to go away. So we have QVB equals mv squared over r. All right, so I want you to do a little bit of algebra magic. I want you to solve the left-hand side as charge over mass, Q over m, and then put everything else to the right-hand side. Let's see what we get. Pause the video, do a little algebra. All right, real simple stuff here. One factor of v goes away, and we're going to get q over m equals v over rb. And this is the version we're going to box in. Now, this only works for point charges moving in a uniform magnetic field. But what do you mean it works? What is this getting us? Okay, well, let's see what's going on. So this mass spectrometer is often used to figure out the masses of objects, charges that are coming out of a chemical reaction. So it's very often that we know the charge on these ions that are coming out, and through other means we can measure the speed of them. So we got the charge, we got the speed. Magnetic field is something you can usually control from some laboratory magnet, and then R, well, that's measured as the radius of the circle. Remember, it's going to come in here, trace out part of a circle. We can measure the diameter, take half of that to get the radius. The only thing left is the mass. This is a mass spectrometer. This is the way to measure the mass of ridiculously tiny objects. Back when we first introduced the masses of the protons and electrons, these 10 to the negative 27 kilograms, 10 to the negative 31st kilograms, you say to yourself, how could you measure the mass of something like that? You can't just pile them on a scale. This is it. A mass spectrometer is a device used in a lab to measure the masses of ridiculously tiny objects as long as they have a charge. Set up a uniform field, introduce these point charges with a certain velocity you measure, and get the mass of it. Now, it often happens in a chemical reaction that different isotopes of these charged objects are created. Isotopes have the same charge but different masses, and so if everything else is the same, they have the same charge, they come with the same speed and the same magnetic field, each different mass will have a different radius. So all these charges will come in, and then by different masses they're going to hit at different radii, or different diameters on this detector screen, forming a spectrum of hits. This is a mass spectrometer. And so each hit there correlates to a different radius, correlates to a different mass. Alright, we'll end today's lesson by just doing some practice problems here. So in your practice problems packet, I want you to do numbers 18, 19, 22, and 24. Pause the video, take some time on that, and then come back and I'll just go over a couple of the highlights. Alright, 18 and 19 are incredibly straightforward. You have the answers. I don't think I'll have any trouble doing it. They're clearly sort of mass spectrometer sort of problems there. Charge moving in a uniform magnetic field. Great. For 22, it gets a little interesting here because you asked for circumference, but it's still a proton. It's a tiny charged object entering a uniform magnetic field. So we're doing a mass spectrometer sort of thing. It's going to be Q over M equals V over RV. We're solving for circumference, but circumference is not in the problem here, so we really want to solve this for R. Let's do our algebra rearrangement. Hopefully you did that, right? So R equals MV over QB, and obviously it looks a little bit different if you have VM on top, it's the same thing. If you have BQ on the bottom, it's the same thing. You know that, right? You know your rules for algebra. So you put your numbers in, and you'll get a radius of 7.3 times 10 negative third meters, which is 7.3 millimeters, or 0.73 centimeters. But it's asked for circumference, right? Circumference, hey, 2 pi R. Put the numbers in, you have no problem getting 0.046 meters or 4.6 centimeters. And of course, it's a 2 sig fig problem, so make sure you have 2 sig figs in your answer. 24 is also a little bit tricky, I guess, right? So here we got alpha particle, which I'm telling you is a doubly ionized helium ion. That phrase shouldn't be too confusing because we've done other problems that tell you some things about that. If you want to go back and see, we've used this idea of the ionization. We want to find the magnetic field that's going to cause it to happen, but we have all this other information. Let's just, okay, we have a charge that's going to enter a uniform magnetic field. We know we're doing Q over M equals V over RB. We're solving for magnetic field, so V equals MV over QR. But let's see what we have, right? All right, we're given the mass. That's good. And we got the charge because it's doubly ionized. We know that. And the radius is given. Ooh, but we don't have the speed. But we do know this. Before it ever enters the magnetic field, before it does, it's accelerated by 1 kilovolts of voltage. So we should be able to find the speed from that. So if you didn't get this far, pause the video, try it on your own. Okay, so hopefully you went with an energy approach. So if you didn't, well, think about this, right? Maybe there's oppositely charged parallel plates with 1 kilovolt. Make sure we see that, right? It's 1,000 volts between them. And of course, the charge is going to accelerate. It's going to gain kinetic energy at a loss of potential energy. Gaining kinetic energy, change in kinetic energy is, of course, final minus initial. And remember, change in potential energy is Q delta V. What's delta V? Delta V is voltage, right? Voltage is defined as delta V. So maybe you didn't get this far. Now pause the video. See if you can solve it on your own from here. Okay, we'll assume it started from rest. Okay, you know it's going to be 0. But what about the charge? It says it's doubly ionized. What does that mean? That means it's lost 2 electrons, right? So its charge is positive 2e. The negative is part of the equation. This just comes from concentration energy. In fact, if you had started with Ke naught plus Pe naught equals Ke final plus Pe final, and then rearranged, it gets this exact same sort of thing. You should have no problem with the right signs here. This negative is part of it, right? Gain kinetic energy and a loss of potential energy. Kinetic energy is, of course, 1/2 mv squared. And you know I'm always a big fan of rearranging algebraically first. So Vf equals negative 2, because that's from the 1/2, times 2e, that's the charge, times delta V over m. You say, wait a second, negative under the radical, we can't have that. Oh, but wait a second. Think about how this works, right? If this is a positive charge and you let it go between the plates, where's it going to go? To the positive plate or the negative plate? It's going to be where the negative plate. Where is it going on the mountain? Oh, it's been a while, right? Remember, potential is like the elevation. So it's going to the negative plate. That's a lower elevation. It's going down the mountain. So is it gaining or losing this 1,000 volts? It's losing, right? And so here's the charge, 2 times the elementary charge. The negative sign is part of the equation. And then delta V is negative 1,000 volts. It lost 1,000 volts as it came down the mountain, speeding up. The mass is given, we should be getting this as the speed, and from here it's just a matter of putting it in. You should have no problem getting the 0.13 Tesla. Ooh, this was a good review.